Okay. Okay. Sorry. Any other questions? Okay. So good. Now let me leave this here. So something that I very briefly mentioned on Tuesday but want to discuss a bit more now is a change of basis. So let's consider the case of 4 sigma particles. Okay. And this is a 2-dimensional Hilbert space. So with basis vectors given by the possible outcomes here, A can be 1 or psi. That's a basis. Okay. There's another basis in which I fuse these two first. Okay. The second and third ones first. They have some fusion outcome B. Again, B also is 1 or psi. Okay. Now, this is a basis of 2-dimensional Hilbert space. According to posit, A is 1 or psi. This is a basis of a 2-dimensional Hilbert space with B is 1 or psi. They're the same Hilbert space. After all, it's just a collection of 4 particles, the same 4 particles. But it's not necessarily the same basis. Okay. So there has to be some basis change. So this is one basis for 4 sigma particles. This is another basis. Right. The basis change is what's called the F symbol or F matrix. Okay. And the standard, I've written it as, I've emphasized the matrix indices A and B on this matrix, but actually the standard notation is also to make sure to specify what particle types you have. So it's a matrix in the sense that it has indices A and B corresponding to the basis vectors in the 2 different bases. And then it also has indices, 4 other indices corresponding to the 4 particle types you can have over here. So I've written down for you F sigma, 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 that matrix, which has to be a 2x2 matrix. But there are also other basis change elements, things like F sigma psi, sigma 1, let's say, etc. Okay. In this case, this is a 1x1 matrix. If you write down the corresponding diagram, so this is just a number. Okay. So in general, so this is a special case for Ising anyons. This is sort of the one most non-trivial one of the F symbols. They all involve fusing 4 anyons. So the one sitting down here has to be, of course, one of the possible outcomes of fusing the 3 up here. And then you have, in the Ising theory, at most a 2x2 matrix. And for most choices of these particle types, a 1x1 matrix. Okay? But in principle, this ranges over all the particle types of the theory. Okay, yes? Yes. Okay, so this okay. Now in principle, in principle, at least, these are always 3 by 3 matrices. However, most of those possibilities are 0 because the only thing that can appear here is a sigma, and the only thing that can appear here is a psi. So it's really a 1 by 1 matrix. So it's really, if you want to write out the indices, it's a sigma here and a psi over here. The A and B indices, A has to be sigma and B has to be psi. And it's just a number. Okay, yes? It always has 4 inside the bracket. That's correct. Oh, yeah. The rule for raising and lowering indices is taking an antiparticle. So in fact, sometimes you will see it with this index moved up here. In the case of the Ising anyons, sigma is equal to sigma bar. It's its own antiparticle. But in another theory, if you moved it up, you'd put the antiparticle over here. Yeah. Exactly. It's just turning your downward-facing line into one of the upward-facing lines. Exactly. Yeah. Any other questions? Yeah. Yes, there's a gauge redundancy here because we said here's one basis and here's another basis. And let's say consider the state in which these fuse to psi. Well, the phase of that state is not fixed by anything, right? I have a state vector in Hilbert space. I can multiply it by an arbitrary phase, right? And it's still physically the same thing. And similarly with any of these. So there's some freedom to redefine phases. I think the gauge redundancy is just can be entirely put into phases. Yes. Okay. Good. So. Now, these Fs we're not free to choose. Now, of course, for Ising anyons, there is some particular set of Fs associated with that theory. And actually, this basis change you can understand in the language of Majorana zero modes. But I'm not going to, well, we'll come back and revisit that in a bit. But actually, there are consistency relations if you, let's say, tried, well, let me just take a guess of what these Fs had to be and didn't want to do the work of trying to compute them from some microscopic theory. Not every guess is a good guess because these things have to satisfy some consistency relations. The most important of which is called the Pentagon identity. Which basically says, so let me take one of these situations where I'm fusing 1, 2, 3, 4 different anyon types into something over here. And let's apply the F moves in 2 different ways. Okay? And if this all is supposed to be a consistent basis change, then they have to satisfy a self-consistency relation. So let me first do that. So I've applied the F move over here to move this line over to here. Okay. And then I can apply it again. To get to here. But that's not the unique way to get over there. I could instead. So you see the first time I moved this line over here with an F move, but I could have done this one first. Move this over to here. Okay, move this line over to here. That's one F move. Apply another F move. I can move this line over to here, and it'll carry along with it whatever is attached to it. To get that picture. And then another F move will move this line over to here. Okay. So it's called the Pentagon because there's 1, 2, 3, 4, 5 different Fs appearing here.
Could you just say what you're doing? What you're doing
yeah. Yes. Yeah, good. Okay. So here are these are states with A, B, C, and D anyons, 4 anyons whose total topological charge is E. Those are all fixed. So this is, if you wish, think of this as a planar situation, A, B, C, D. 4 anyons here whose total topological charge, which I can measure on the boundary, is E. Okay? And what I have here is some basis of those in which F and G are fixed. Okay, those are some bases. So if I pick some value of F and some value of G such that the fusion rules allow this, then I'll have a basis vector in this 4-particle Hilbert space. Okay. Now what the F move is the basis change in that Hilbert space. So it's A, B. Okay. So here A and B are still fusing to F, but now instead of the different possible values of G, it's whatever the fusion outcomes are here. Let's call them H. So I now have a new basis, same 4-particle Hilbert space with fixed total charge E, but it's a different basis, and F is just a basis change from this basis to this basis. Okay? They're both perfectly good bases. There's nothing preferred about one as opposed to the other. So there should be a basis change between this and this. And then finally, I can do and now this is H and this is I. So I've done a basis change now to one in which C and D have a fixed fusion channel H, and then H and B have a fixed fusion channel I. So in all these pictures, A, B, C, D, and E are all fixed, okay? And F, G, H, I are all ranging over the possible particle types in the theory to label the different basis vectors, okay? To give labelings of basis vectors in this Hilbert space, in this 4-particle Hilbert space. So there has to be some basis change from here to here, okay? Since after all, the two bases for the same Hilbert space. And one way to figure out that basis is to see that it's a product of two Fs. Okay. However, you can also see that it's a product of 3 Fs if you take this other route, and those had better give you the same basis change, right? Because you're going between the same two bases. Yes.
By symmetry, the top of the metric
Mm-hmm. Yeah, that's a matter of taste. I don't think there's really a preferred basis. This basis looks nice, I agree. So you might prefer it, but I mean, look, it's just a different basis in a Hilbert space. I mean, ultimately, we're going to talk about encoding quantum information in them later on. So there may be one or another basis that's sort of more natural in terms of having an interpretation in terms of qubits or something like that. So this might be kind of nice for some things. But really, it's whichever basis is most convenient. Usually people do things, like to draw things in terms of this basis. But there's plenty of circumstances in which this is a very nice basis. But I don't see any sense in which one's preferred.
I guess my general question is symmetries don't really matter.
No, it depends on the physical situation. There may be some reason that you have the particles arranged in your system in a certain way, and you want to do certain things so that certain of these bases are more convenient. But it's not a matter of symmetry. It's just a matter of convenience, either for calculations or for some experiment. It really is convenience. Yes. It's a 2x2 matrix, correct? Yes, it is. And we're actually going to figure out what it is by solving this equation right here. I'm going to give you 2 arguments for what its explicit form is. Okay? Yes. Well, the left-hand side is quadratic and the right-hand side is cubic. Okay. Good. Yes. 3x3 with several zero. You could think of it as 3x3. There's 3 particle types in this theory. So in principle, all the F symbols in the Ising theory are, in principle, they're 3x3. But since we know that not all of those can appear, it's really a 2x2 matrix. Yeah.
So
Yes.
here, depending on which only the same difference?
No, it's not. It's not. That's correct. It's not. You'll see. Because like this move over here, you can see this one involves F, C, D, and E over here. But this one over here involves a different set, right? This one involves A, B, H, and E, for instance. Yeah. So it's not the same indices appearing on these things. So actually, as an illustration, let's do this for Ising anyons. Let me put some labels on here. Okay, so let's put psi. Okay, so psi coming in here, then sigma's over here. Okay, so over here, psi and sigma has to fuse to sigma, but then over here, this is free. Okay, so this is a two-dimensional Hilbert space. A, which can be 1 or psi. Those are basis vectors in this Hilbert space. This has to be a sigma again, but now this is a new basis over here where B can be 1 or psi. And this basis is related to this basis by F. And then over here, this is B, this is sigma. So really here we're going to be doing a 1-by-1 or diagonal F move to get from there to there. Okay. Over here, so this has to be A. Okay, so this hasn't changed over here, A. Now we move this sigma over to here. We have an A here, and then we can call this C. But in fact, C is not really free because after all, psi and C have to fuse to A. So if A is 1, then C has to be psi, and if A is psi, then C has to be 1. Okay, so these, even though I'm going to for the moment call them separate labels, just keep in mind that they're not really different. Okay, and then over here we have D, and then oh no, sorry, this is C. This one is C. Sorry, and this is D. No, this is sigma. Okay, yeah. Okay, so the first F move, so let's write this out in equations. The first F move is F sigma, 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 sigma AB. Okay. The second F move is F sigma psi B sigma. No, psi sigma. Sorry, psi sigma B sigma. Okay, which is diagonal. So it's sigma sigma. Okay, so that's the left-hand side of the equation. That's the quadratic side. The right-hand side of the equation is this one. So that's F let's see. So we're moving this line over to here, so that looks like psi sigma sigma A, right? Okay, and that's this move is F psi C sigma sigma, and then the last one is F from C to D, C to B. Okay. I think that's right. Okay. Yes, they're both 1 by 1. This is a sigma, sigma, and sigma, sigma, but correct. Oh, is it sigma C? Okay, yeah. Okay, right, thanks. Okay. Good. Now, so let's take a look at this one. This is, so this, if I boil this one down, it's the psi sigma B sigma is equal to this thing times okay, which I can redraw slightly, okay, since this intermediate line here is a sigma and this is a sigma. Okay, so this is what, if I just focus on the piece of the picture that this basis change is doing, it looks like this. And I'm going to redraw this to make it okay. So it looks like this. If B equals 1, okay, if B equals 1, this should obviously just be 1, because the one line you can just get rid of, right? One lines you can just, you don't even have to bother to draw them in principle, okay? So if B equals 1, so this thing should be equal to 1 for B equals 1, okay? Now, for B equals psi, okay, we can take a guess to what it should be and then try to see if the consistency works out. The natural guess for B equals psi is that it should be -1, or a natural guess, because what you're doing is, if you look at what's happening from the left to the right-hand side of the equation, you're moving two fermion lines past each other. And so a natural guess, so a guess here would be, guess is that it's equal to -1 for B equals psi. Okay. Now, again, this is just a guess. We're just trying to find consistent solutions to this equation, but that's a very natural and reasonable guess. Okay. Now, over here, if you'll recall, A and C really had to be opposites of each other, if you remember, that because after all, C was kind of a dummy index here because psi has to fuse with C to give A. So a very natural guess here, so it's not a guess. So A and C have to be opposites of each other, right? So, and we could always try as a guess to just set all these things equal to 1. Okay. A and C are really the only free, quote unquote, free things here. And A has to be the opposite of C. If A is 1, C has to be psi, and if C is 1, A has to be psi. In principle, there can be phases and so on here. But maybe the simplest thing to guess is to guess that this is just off diagonal ones. Okay. This one. So what's that? Let's just see. So that one is, that's this F move over here, right? And we're just moving this line over here. So the outside indices to me looks like psi, C. Oh, the outside index is A. You're right. Thanks. Yeah, the outside index is A. Okay. Okay. But again, a natural guess, which we can check for consistency, is to take this equal to 0, 1. We know it has to be off diagonal. We know it's a 2 by 2 matrix because there's just A and C here. So in principle, we could put some phase here and the opposite phase here. But let's just try the simplest thing. Okay. So if we do that, and if we make this guess of this -1 for pulling one fermion line through the other, the other thing you'll notice is we made this kind of intuitive argument that when B equals psi, you're moving a fermion line through each other. You can check similarly that no fermion lines are moving through each other in either of these. So the reason that we used for guessing a -1 doesn't exist over there. So what that says is if I suppress indices and write these as just matrix equations, right? That's what, so this equation that's quadratic on one side and cubic on the other side, because as someone asked, it's not the same exact F symbols that are, or F matrices that are appearing in each of those factors. The left-hand side becomes the F that we're probably most interested in times this, and the right-hand side is this times that same F that we're most interested in. Yes. Yep.
If you had some concrete
Yep.
implementation of Ising,
You would just calculate it from microscopic. You would just calculate these things microscopically.
so
Correct.
you could do a calculation.
Yep.
You wouldn't have to worry about the Pentagon identity.
Correct.
You guarantee that what you got would satisfy.
Correct. Unless somehow the physical assumptions were wrong and it was not a topological phase for some subtle reason, right? Yeah.
But what you're trying to do is you're trying to construct this
without having the physical realization. Yeah.
conceivable.
Yes.
Might you be able to realize.
Correct.
So
And in fact,
one version, you have different F matrices.
well, yeah. So in fact, these are. I mean, when you exercise the gauge freedom. So I'm not doing the. I'm giving you kind of the flavor of it. But when you kind of exercise the gauge freedom and apply the Pentagon, because I can make many choices of what's sitting out here, it turns out that there aren't many solutions. It turns out the structure is extremely rigid, and the solution I'm writing down is actually almost the only solution. Okay. Now, I mean, we'll see that there are, for instance, for the exact same, all I'm really inputting here is the fusion rules. So for the exact same fusion rules, you could have Ising anyons or the opposite chirality version of the opposite Ising anyons. Both of those should pop out as possible solutions. Okay. Because I haven't put in any physics yet here, but the number of solutions is very limited, and yeah. So this is a highly constrained, yes.
To which extent you obtain a matrix equation, or to which extent it's a matrix product? Because from the upper panel, the indices are not overlapping.
Oh yeah, so. I'm writing it as a matrix equation. There's no summation on B here. However, I'm taking, this is really just a number depending on B, and I'm writing that number as a diagonal matrix. So this is a slight cheat because I'm really just saying I'm multiplying by a number that depends on B, and I'm writing that number as a diagonal matrix. This really is literally a matrix equation because C is a free index that's, I mean, if we know that C is not really free, but I'm treating C as a free index that's summed over. So actually, the correct way of writing this is sum over C.
Contracted with something inside the bracket.
It does. Yeah. Okay. But once we get to this stage, now we're happy because this tells us that f has to be equal to, f is just the change of basis from like a spin in sigma z basis to sigma x basis. Okay. So what this is saying is just for this particular Pentagon identity with this particular set of external particle types, a consistent solution is to take f sigma 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 equal to this, f this one psi sigma equal to -1, and all others equal to +1. Okay, so far we've only applied one possible set of the Pentagon identity, one particular choice, and we made some guesses. We made a guess of a -1 here, and we made a guess that these are 1 here. That guess is equivalent to saying we have a consistent solution to this equation in which f psi sigma is -1. All the other f's, which are all the others are 1 by 1 matrices, are equal to +1, and this is the one other non-trivial. So two non-trivial ones, all others +1, is a consistent solution to this equation. If we apply the other possible choices of external legs, we'll see that in fact this is the only consistent solution to this equation. You would have gotten stuck. Exactly. Yeah. Yes. Mm-hmm. Yeah, I've combined these two. These two are really not matrices. These are numbers. And all I've really used is the fusion rule, which tells me that C and A have to be opposite. If C is 1, A is psi, and vice versa. To write this sum over C as a matrix multiplication. And then I have a choice of what that number is that appears here. And we made a guess that that number is equal to 1, which is tantamount to guessing that both of these F symbols are just 1. Okay. Okay. So now, again, we wouldn't have to go through this exercise if we had a microscopic model in mind. And indeed, if our microscopic model were just 4 Majorana zero modes. So as Nick discussed yesterday, these zero modes arise as solutions of the Bogoliubov-de Gennes equation for a P plus IP superconductor and in other similar contexts. So if we kind of follow that Reed and Green philosophy to Ising anyons, then these are our Ising anyons. These are our 4 sigmas, okay, and this basis, okay, of 1, 2, 3, 4. This basis A is the basis of I gamma 1, gamma 2 equals plus or minus 1, okay. The other basis over here is the basis of I gamma 2, gamma 3 is equal to, which is equal to I gamma 1, gamma 4 is equal to plus or minus 1, okay? Because I'm assuming the total fermion parity is 1 here, okay? So the F move is just supposed to do the basis change between these two different bases, okay? But I can represent, in this two-dimensional space, I can represent sigma is I gamma 1, gamma 2, sigma z, and sigma x is I gamma 1, gamma 4, and sigma y is I gamma 1, gamma 3. And then you can see that indeed the basis change between this basis and this basis should be exactly that basis change over there. Okay. So again, as Charlie pointed out, if we have a microscopic model, which we do in the case of Ising anyons, we have the Reed and Green model, then we can just work with these solutions of BDG equation, okay, look at their algebra, and then we can deduce what this basis change is here, because it's basis change from the eigenvalues of I gamma 1, gamma 2 to the eigenvalues of I gamma 1, gamma 4. Okay. But if we didn't have that microscopic model and we want to proceed more, we want to proceed more abstractly, we could solve the Pentagon identities. Yes. Mm-hmm. Oh yeah, so no, that's a good question. So so there is gauge degree of freedom that I think I mentioned in answer to an earlier question of yours. So you have to check if they're gauge equivalent to each other. So the simplest way I would say to do that is to compute some physical things. So the F right now isn't physical, but you could compute an amplitude for something. Okay, take a braiding process where you take two particles and braid them and ask what you get. So you'll in order to do that, you'll have to combine F's and R's in some way. So I haven't talked about the R's yet. So so the short answer is compute physical. The abstract answer is see if you can turn one into the other by applying some gauge transformations, which are choices of phases associated with each of the particle types. Okay, defining those. Basically, every vertex like this, you can assign every vertex A, B, C. In principle, with a mu, you can assign a phase to that particular vertex because that's a basis state on the three-punctured sphere. And you can choose phases there which transform all these F symbols and R symbols and try to see if you can map one solution to another. But I would say that probably the more intuitive, so that's the correct answer, but the more intuitive answer is compute some physical process. Those things, of course, shouldn't depend on the gauge. Okay. Any questions? Yes. Mm-hmm. Yeah. That's right. For fixed total fermion parity, this is a two-dimensional space. And so I certainly have Pauli matrix operators on any two-dimensional space. And what I'm saying is the algebra of these, yeah. They square to 1 and they anti-commute. Exactly. Yes. So I haven't talked about braiding yet. Okay. There's
no other relations involving
only fusion.
Only change base.
Correct. That's right. So I'm about to talk about braiding, where you have the hexagon, which I'm about to write down. But there's a theorem called the McLean coherence theorem that states that pentagon and hexagon are sufficient consistency conditions. And for only fusion, as Nick said, it's pentagon sufficient. Okay. So if you remember, we talked about the R matrix, which, let me write that over here. Okay. So those are consistency conditions for F, but F and R have to have some consistency conditions. Okay. We can again play this game of starting from some initial state and going to some particular basis, going to another basis, which will involve both implying F moves to change basis and also R moves, which introduce some phases due to braiding. So if we start with such a basis, apply an R move, we get this. Then do F. And then R again. This illustrates, actually, the top half of the hexagon illustrates how you can use F and R to do braiding. So here we have two particles that are undergoing a counterclockwise exchange. And what you can see is we'd like to use R to tell us what happens, but the fact is we don't know what the fusion channel of these two lines is. So we use the F move so that we write this state as a linear combination of states in which there is a definite fusion channel here. And then you can apply R to that. Okay? So you can use F and R in combination to compute braiding. On the other hand, we could have done an F move first. Okay? In which case, this would look like this. Now, if you look at this picture, if we just pull this line down, and without doing any move at all, this is just equivalent to this picture. I'm just taking this line and moving it like this. I haven't done any braiding or change of basis. Sometimes people consider this to be a separate move and call the hexagon a heptagon, which is actually appropriate in certain circumstances. But the standard here is to call this the hexagon and not treat this as a separate move. Now we're in position to what's that? You're right. Yes, thank you. Too many lines there. Thanks. Yeah, too many lines. You're right. So this is equal to this. We now apply R. And then finally an F. No, I can't raise this. Now again, we can use this to constrain the F's and R's. If we had a microscopic model, we'd be able to, of course, just do that for a microscopic calculation. However, in this case, sometimes the R's actually aren't that easy to figure out, to really nail down. And this does a nice job of fixing them. So let's apply this again to Ising anyons. So with all sigmas. Okay, so let's call this A. A can be 1 or psi. This is still A. We now have a B that appears here, and this is still B. So it's a change of basis from A is 1 or psi to B is 1 or psi. Over here, make a change of basis here to a C, which is this, and then make that change of basis over there. Okay, so so if we now apply, you can see the left-hand side of this equation, if I do for the top, is R times F times R, and the bottom side is F RF. So what we have over here is R sigma sigma A. Okay. Now, is that correct? Yeah, it's R sigma sigma A. Then we have an F move, okay, which is F and then we have an R again, which is R sigma sigma B. This has got to be equal to, on the right-hand side, we have an F move. AC. We do an R. And then, oh, wait, hang on. Is that right? No, it's R sigma C sigma. and then F. Okay. So these are, so this is the hexagon. I can multiply out the right-hand side. Okay. So this looks like the matrix 1 over the square root of 2 r sigma sigma 1 squared r sigma sigma 1 . Okay. I just multiplied out the right-hand side, the left-hand side. Okay. Letting A equals 1 or psi. So I have this 2 by 2 matrix over here. Okay. The right-hand side, okay, this C over here can be 1 or psi. And if I multiply that out, I get and then up here I get R and then the same thing over here. Okay, that's just multiplying out. Here I'm treating this. This is just a number depending on what C is, whether it's 1 or psi. I've treated it as a diagonal matrix, which I can do since it's just a number. And then I multiplied out the F's on this diagonal matrix to get this. Over here, I have the F, and then I multiplied on both sides by these numbers, which I just treated as diagonal matrices, and this is what you get. Okay. So you can see that you have something quadratic on the left-hand side for the R's, since in this case we know the F's, having solved Pentagon. And on the right-hand side, you have something linear in the R's, and it's not even the same R's. Okay. Now, R sigma 1 sigma, that has to be 1, unless one took an extremely perverse choice of gauge. Okay, right? Because that's just saying, let's take a sigma and a 1, and let's take 1 around the other. You should get 1. R sigma 1 sigma is the square root of that. So in principle, you could have tried to mess it up by making a bad choice of gauge. But let's not do that. Let's not make our life any harder than necessary. So that R sigma 1 sigma is just 1. Okay. Now R sigma psi sigma. Okay, well here we're going to take a guess and try to make this equation work. Okay, of course we'll then have further consistency conditions from applying hexagon to other choices with sigmas and psis all over. But a very natural guess here is that what is this? This is taking a psi around a sigma, and if we think of a sigma as a vortex and a psi as a fermion, you're supposed to pick up a minus sign. So this, you might think, a natural guess for this would be plus or minus I. Okay, both choices are equally good. I'm going to just choose minus I because I know what the answer is, and I'm making a particular choice of chirality here. If I had chosen plus I, we would get the opposite chirality solution. Okay, but again, this is just a guess, right? And we have to, and in principle, you could have put anything you'd like, any phase you liked in here, and tried to see if the equations would be satisfied, and you would down the road find some contradictions had you chosen anything else. Okay. So we've, well, actually, there's another reason to choose something like an I over here, because if we look at the left-hand side of this equation, this is a pure phase, right? R sigma sigma 1 is a phase. I've squared it. It's still a phase. So this thing over here, it actually better be a phase, right? And since this is 1, that means this had better be I, given the normalization square root of 2, plus or minus I over here. Okay. So actually, just consistency, this consistency equation by itself really tells us this has to be plus or minus I. And the nice thing is that that actually accords with our intuition that psi is like a fermion and sigma is like a vertex, and you should get a minus sign when you take one around the other. Okay. Any questions? Yes. You're right. Thanks. And so on. Yep. Okay. So now we know this is e to the pi I over 4. This one is e to the minus pi I over 4, e to the, and so on. And now we can solve for the left-hand side. Okay. And that tells us that, in fact, the only consistent solution here is R. Well, a consistent solution, I should say, is e to the minus pi I over 8, and R sigma psi is equal to e to the 3 pi over 8. Okay. So, I mean, the only reason I say it's not the unique solution is because this is quadratic on this hand side. So I guess there could have been extra minus signs appearing here. Okay. Now, if you look at this solution and think back in terms of, here are some zero modes, gamma 1, gamma 2, and what we're doing is we're braiding them around each other, then I could rewrite this as this whole thing as this, where I gamma 1, gamma 2 equals plus or minus 1 corresponds to 1 or psi. Okay. So again, if you have the microscopic model, like if you have quantum Hall wave functions, then of course you can just work within the microscopic model, derive what these things are out of the microscopics, compute Berry phases or matrices, and so on, as Nick described yesterday. But on the other hand, what you can do if you don't have a microscopic model and you're trying to study this abstractly, use the hexagon identities I just did, and then you find that these are the R matrices. Okay. You could write that in terms of the underlying Majorana fermions if I wanted to represent it in that way, and you could summarize both of these symbols by saying it's a phase e to the pi I over 8 times this piece over here. Okay. And actually, if you are using the superconducting language, it's not hard to convince yourself of this part, but this part actually isn't easy to derive. Okay. Any questions? No. There was a Z2 ambiguity here just because of the way, because these things in this particular pentagon, in this particular example of the hexagons, since this appears quadratically, there was a minus sign ambiguity here, which would get resolved later if we applied more hexagons. There still are U1 ambiguities associated to fixing the gauge in both of them, in principle. Okay. So that's Ising anyons. Okay. I want to talk about another type of non-abelian anyons. Fibonacci anyons, which are either the second most or second simplest or first simplest type of non-abelian anyons. It's simpler in the sense that there are only two particle types. Often denoted 1 and epsilon. The fusion rule is very simple. Since there's only one non-trivial particle type, there's only one fusion rule that we have to bother to write down. And it's epsilon times epsilon equals 1 plus epsilon. Yes?
Are there NLP solutions of non-abelian?
There are. So I'm not going to talk about non-abelian Chern-Simons theory here. But, well, actually, the description of a P plus IP superconductor that Nick gave yesterday is one type of effective field theory description of non-abelian anyons. But I think that you're probably asking, is there a description that sort of only has the low energy, kind of topological degrees of freedom, and there are non-abelian Chern-Simons theories? Okay. So there's just one non-trivial fusion rule. If we write this fusion rule as a matrix, for n epsilon, it's this matrix because you take 1, you fuse it with an epsilon, you have to get an epsilon. You take an epsilon, you fuse it with an epsilon, you can get 1 or epsilon. Okay? So it's this matrix. The eigenvalues of this matrix are 1 plus or minus the square root of 5 over 2. So one of the eigenvalues is negative, but the other one, the larger one, is positive, and the largest eigenvalue is the golden ratio. Okay? Square root of 5 plus 1 over 2. So what that means is if we take a collection of Fibonacci anyons, okay. So suppose we take a collection of n Fibonacci anyons. The dimension of Hilbert space goes as the golden, so this is n Fibonacci anyons. The dimension of the Hilbert space goes as the golden ratio to the nth power. Okay. Now, we can actually compute what it is exactly. Okay. So let's say we want the number of, let me call this k. I want to use n for number. Suppose we have n, we want to know what the number of Fibonacci, number of states is for k Fibonacci anyons whose total charge is 1 over here. Well, that's just equal to the total number of Fibonacci anyons, the total number of states with k minus 1 Fibonacci anyons whose total charge is epsilon. Okay? Because if you had k minus 1 whose total charge was 1, of course you couldn't get 1 at the next step because you add an epsilon, you have to get epsilon. On the other hand, you can get 1 if the total charge with k minus 1 was epsilon. Okay. And all the ways that you can get this come from this. On the other hand, if I ask, well, how many states are there of k anyons whose total charge is epsilon? Well, if you had k minus 1 whose total charge was 1, you add another epsilon, you can get total charge epsilon. But also, if you had k minus 1 whose total charge was epsilon, you can add an epsilon and get epsilon. Okay. But notice, n sub k minus 1, 1 is in fact through this relation equal to n sub k minus 2 epsilon. So what you now notice is that the exact number satisfies the recursion relation for Fibonacci numbers. That you get the kth one by adding the k minus 1th and the k minus 2th. Okay. Yes? Here, this is number of particles and this is total charge. Okay, so k particles and this is total charge. So if you, for instance, if you take two Fibonacci anyons whose total charge is 1, there's only one such state. If you take 3, there's only one such state because these two confuse to epsilon, fuse that with an epsilon. Okay. Total charge 1, there's only one such state. On the other hand, when you arrive with 4, these two could fuse to 1 or epsilon. These two could fuse to 1 or epsilon. That'll still let the whole thing have charge 1. So now there's two states. Okay. But now when you go to 5, okay, there are 3 states. And so on. So you get the nth Fibonacci number in this way. Or kth Fibonacci number in this way. Exactly according to this recursion relation. Okay. Yes? The total dimension of Hilbert space is an integer. It's the kth Fibonacci number according to this relation over here. So it's with 3 Fibonacci anyons, the total charge 1. It's 1 state, it's 2 states, 3 states, 5, 8, 13, and so on. That's the asymptotic form, exactly. So the nth Fibonacci number goes as the golden ratio to the nth power.
Even though it's still
Correct. This is definitely an integer. And this is just the asymptotic form of it. Yeah. Right. Yes, there is, because total charge 1 is related to total charge epsilon for just one less particle. So the same sequence applies, just entirely shifted down by one step down the sequence. You're right. Sorry. So I could have done the epsilon sequence, which has 2 states here, because these two can fuse to 1 or epsilon, and then they fuse. You got 2 states there. Here you get 3 states, and so on. Yeah, that's right. You're right. Sorry. So I demonstrated the one that I didn't explicitly write. Okay. So we can go through the same procedure we did for Ising anyons with the Pentagon and Hexagon. There's only one non-trivial F symbol. It's the one with 4 epsilons, and it's equal to this matrix in terms of the golden ratio. There are 2 non-trivial R symbols. Again, you can obtain these from the Pentagon, Hexagon. So that's the data that you need to understand, basically, to do computations with Fibonacci anyons. Okay. Analogous to Ising anyons, a little bit simpler in the sense that since there's only two particle types, there's not, everything is at best, is at worst, sort of 2x2 matrices in terms of the basic data that you're using. More complicated in the sense that we don't have this beautiful free fermion model that we can always, with Ising anyons, we always have this free fermion, Majorana zero mode picture that we can always use for intuition, to bail us out if we get stuck. We don't have that with Fibonacci anyons, but it's got the other simplicity. It's only two particle types. Okay. Any questions? Yes. Well, that's a good question. Let me return to it later. But the short answer is there definitely are concrete ideas for how you could realize Fibonacci anyons in nature, or at least in models. One is due to Nick and Ed Rezai, which is basically suggesting that the 12/5 fractional quantum Hall state supports Fibonacci anyons, or a slight variation, not exactly this, but something very closely related to this, slight variation on Fibonacci anyons. There's another construction, a coupled wire construction due to Charlie and Jeffrey Teo, which also has I don't know how realistic you can call that, but it's very concrete of what you would do in a system of coupled one-dimensional wires to get Fibonacci anyons. Yeah. Mm-hmm. I mean, it probably does at some level, but I don't see it very directly, to be honest with you. Yeah. Oh, yeah. Well, they don't let fives in them, but the one that's Fibonacci does, and I think that's not really a coincidence. I think that is related. Because the next one, in principle, would occur at, denominator 6. Oh, no. Oh, no, even for k equals 3, I guess. Oh, that's true. Yeah. Yeah. No, you're right. Yeah. But this may be the first one, and the others you can sort of just do an abelian composite fermion on top of it, sort of. You can add some flux. Yeah. No, you're right. Yeah. Okay.
The filling factor
Yeah.
has more to do with conformal weights.
Yeah. Yeah. Okay. Yeah. Yeah, I think you're right. Yeah. Okay. Okay, so in the remaining little bit of time that we have, I want to switch gears slightly. Yep.
So how can we come up with fusion rules? Like, can I just write down any fusion rule I want, construct a Pentagon element, which is expressed, or basically a table of consistent fusion rules, and we just borrow from the first two entries from that table?
You could even work without. You don't actually have to know the fusion rules in advance to apply the Pentagon and Hexagon identities. You could just say for a certain fixed number of particle types, let me try to find all solutions of Pentagon and Hexagon. See, the Pentagon, in some sense, already knows about the fusion rules because where you get 0 elements is telling you that two things don't fuse. So the classification program of TQ of topological phase with a small number of particles proceeded just by saying, let's consider theories with 1 particle types, 2 particle types, 3 and 4 particle types, and just solve. And this is work of my colleague Zhenghan Wang and his collaborators, that if you just start with 2, 3, 4, and 4 particle types with no other assumptions and just look for solutions of Pentagon and Hexagon, you only get finite number of solutions. So you didn't need to put in the fusion rules as an input, actually. Well, it's only been shown up to, oh yeah, so it's known that there's a finite number of solutions for any number of particle types. They haven't all been computed. Only up to 4. Well, it depends what you mean by legitimate T. I mean, they're legitimate TQFTs in the sense of they satisfy all the consistency conditions. On the other hand, physical models or even how they relate to a Chern-Simons theory, something like that, isn't known for close.
So they exist. There exist ones that cannot be represented as Chern-Simons.
Well, no, I didn't say that. I said it isn't known whether or not there exist. You know, it hasn't been proven that there don't. Yeah. Right. Well, correspond to something that we already know, a Chern-Simons theory or some kind of CFT or something. It's not known that those all correspond to known things. Yeah. I mean, I know that one of the solutions of this, there's a solution that has total quantum dimension 5 plus the square root of 13 that people don't know what it's related to. It's just some weird oddball solution, but yeah. I don't remember the details, yeah. I think so, yeah. Yes. Oh, yeah, no, you have to do all of the cases. I just, I applied the Pentagon identity just to this one particular case with 1 psi and 3 sigmas. And this one gives you some nice constraints. You should certainly also consider with 4 sigmas or 2 sigmas. I mean, you have to consider they all have to be satisfied. Okay. It's just, for illustrative purposes, I only showed you one because this particular one I know gives you, pretty directly gives you what the non-trivial F symbol is. But this is just an example. This is just one particular application of Pentagon. You do have to satisfy it for all possible external particle types. That's right. Yeah, many of them are going to be just trivial. Yeah. Okay, so in the remaining few minutes, I want to just say a few words about how this all can be applied to quantum computing. Okay. In particular, there's a notion of an error-correcting code, okay, which is basically the idea that you might have, okay, some larger Hilbert space, in principle the Hilbert space of the whole universe, and inside it you want to select a subspace. So this is the total Hilbert space. A subspace called the code space. Okay. And so this is where you'd like to encode quantum information. Let's say if you want to have a quantum computer, you need such a space to encode quantum information. You want to apply unitary transformations to it, which would be your gates, and then you want to measure what happens. And the property you want this to have is, well, okay, there could be errors, which are processes that carry you out of the code subspace. Okay? And you want to be able to diagnose and fix those errors. So what you need for that to occur, or for that to be the case, for you to be able to do that, is that you're not in general going to be able to correct every possible type of error, but the types of errors that you're going to be able to fix are the ones for which this is true, which is, let's say, E sub I is some kind of error. If this is true, which is to say if the right-hand side is basically just the projection operator up to some numbers, and this is not an operator here, this is just numbers, then this is a good code. In particular, what this is telling you is that if you have some states, so let's say A and B are sitting inside this code subspace, then what this is telling you is that if I consider this matrix element, then this is equal to Cij times delta AB. Okay, in particular, what this means is that you aren't going to get from one thing in your code subspace to another. Okay, so you're not going to have an error occur and misdiagnose that a different error occurred starting from a different error in your subspace. Okay, so if an error occurs, you can always get back to the right state. Moreover, the fact that this doesn't depend on A or B tells you that in that process you don't learn any information about which state you were in. So having this is both necessary and sufficient condition for a good code for those types of errors. Okay. Now, I'm writing it in this way because I'm hoping that you would recognize the similarity between this and something we started out with in the very first lecture, which was the definition of a topological phase, that this be some constant like this. In other words, that the definition of a good code subspace is essentially the same as the definition of a topological phase, or at least very similar. So this was kind of, well, this is one way of thinking of the basic insight that Kitaev had that launched topological quantum computing, okay, was to recognize this. So in particular, it suggests that we should think of our code subspace as being these topologically degenerate states, such as the states you have, let's say, on the n-punctured sphere, okay, and that enables you to correct errors. So what kind of errors can you correct? Those caused by local operators up to exponential errors, up to those exponential corrections. Types of errors. So these are, so E sub I is like a type of error that can occur. The types of errors that you can correct, I and J label the types of errors. Oh, yeah. No, sorry. So okay, very good question. So here, all I'm really saying here is that we can correctly identify when errors occur, and in principle, we can correct them here in the code subspace because what we're saying is the errors, for instance, what this is saying is that we can figure out how to fix an error and get back to the correct initial state without knowing what the initial state is. Okay, that's what this equation is saying.
What is that in the context of topological?
Yeah, so in the context of a topological phase, what that means is, look, an error occurs here if you start in one of these topological states. You go out of the code subspace by, let's say, creating a local excitation, okay? And then there's, well, in principle, what you could do in the normal active sense of error correction is you could find a local excitation. You see, oh, is there a local excitation of the ground state anywhere? And if there is, you fix it by annihilating the two quasi-particles. There's a passive sense in which, if there such a thing occurs, then it will decay back to the ground state and maybe emit a phonon or photon or something like that. Okay, so that's assuming that the system, let's say, is in contact with a cold bath, so that there would be a passive sense of error correction that the Hamiltonian penalizes those states. Yes.
I error and E back to the correction of the error.
Well, that's a way to think about it. I mean, you could also think about it as two different errors if you wish. But yes, you can think about it the way you just said. Well, I mean, one way to think about this is an inner product between EI acting on B and EJ acting on A, and saying one type of error acting on B will never be mistaken for another type of error acting on A. No.
Like one error would not mess up all the others.
No, I mean, an error does carry you out of the code subspace. It's just that you can always fix that error and not get back to the wrong state within the code subspace, in principle. Okay. What's that? CIJs are just some numbers that depend on the particular types of errors that occur in here. Okay.
But I mean, in terms of
Yeah. Well, I mean, maybe it's easier to think in these terms. So here are topologically distinct ground states, and you act with some local operator here. There's no, if you act with a local operator, there's no amplitude to get, or exponentially small amplitude to get from one topological ground state to another, right? However, the diagonal, which is to stay within the same, it's not going to be amplitude 1. It's some amplitude that depends on the particular operator. Yeah, but still classical, exactly. Huh? Okay, got it. So, this suggests the following ways of encoding quantum information in, let's do Ising anyons first. Okay, there's what's generally called the dense encoding, which is take two sigma particles, they can fuse to either 1 or psi, and let's call that a qubit. That's two-dimensional space. Now, this is pretty efficient because you only need twice as many sigmas as you have as qubits, but it is also not so great in the sense that if you fix the total fermion parity, then it means you need one extra pair of sigmas to kind of enforce total fermion parity even, let's say. And that one extra sigma pair of sigmas is entangled with the fermion parity of all the others. Okay, so that leads to a lot of kind of awkwardness. There's the more commonly envisioned sparse encoding, which is four sigmas. Okay. The total charge of the four sigmas is assumed to be 1. Sorry, not 1 or psi, just 1. Okay. And then the pairs within, this one can be 1 or psi. And since the total charge is 1, this one has to be exactly the same as whatever this one is. So for this encoding, you need 4 times as many sigma particles as qubits. Right? But the nice feature is that each qubit has total topological charge that's trivial. Correct. 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 That's correct. Yeah.
It doesn't cause difficulty that you have to maintain.
It doesn't. That's right. But I'm about to talk about the analogous things for Fibonacci anyons where actually it can cause difficulties. Those are normally called leakage errors. So this is the computational subspace, which is a 2-dimensional subspace of the states of 4 sigmas. In principle, it's a 4-dimensional subspace if we don't restrict to that. So leakage errors would be errors where you're leaking out of this 2-dimensional subspace to the larger 4-dimensional subspace. That's not really a problem. That's not a major difficulty here. On the other hand, so for Fibonacci anyons, the dense encoding, okay, has 3 Fibonacci anyons whose total topological charge is epsilon, and these two are 1 or epsilon. So that's the dense encoding. And here you can see this is the danger that you're worried about is more present here because when these two fuse to epsilon, it's actually awfully easy for an epsilon and epsilon to fuse to 1 and take you out of the computational subspace. Okay.
Why do you choose epsilon?
Oh, so you would have, if you choose 1 on the outside, then it's unique. There's only one state. So you don't have a qubit in this case. Okay, for the dense encoding. So this is just a special feature of Fibonacci, but yeah, I see your question. Just one sec. So there's also a sparse encoding. Okay, which is 1 here and 1 or epsilon here. So this more mirrors what we do in the sparse encoding for Ising anyons. Yes? Well, you can measure to check that the external one is epsilon, and then try to correct if it's not. Yeah. Well, I mean, what you would normally do is you would initialize your anyons so that you take your collections of 3, initialize by measuring the total topological charge, and then if you get the wrong answer, you could throw it away, or you could do something else and then try measuring again, and you would initialize that way. But then, of course, depending on exactly what gates you do in terms of braiding, you might go out of that subspace. That's the concern you might have. Okay. The nice thing about or unnice thing about the dense encoding is that complete gate set. So what we'd like to do, so this is our encoding of quantum information. We want to be able to have some protection against errors. In all these cases, the protection is this at 0 temperature at least, and in the completely adiabatic limit where everything is done extremely slowly. This is sort of what the power of this is, that if we keep all of these particles far enough apart, then local perturbations are not going to cause errors. Okay. We, of course, also, in addition to the error correction, want to apply gates to do some unitary transformations here. A complete set, in this case, is that braid and that one, which is braid 1 and 2 or braid 2 and 3. With those, that generates everything. And this one is just given us by the R matrices. Okay, it's just that diagonal transformation. And this one over here is, well, we have to conjugate by the F matrices. Okay. So Fibonacci anyons, this is great because with relatively simple braids we can generate anything we like. The problem potentially is that number one, we don't have very strong evidence yet that there's any system in nature that has these, although there is some evidence perhaps about 12/5. The second problem is in principle this generates everything. On the other hand, there are many things that are quite simple that are very difficult to, well, generates everything means that if you do a long enough braid, you can get arbitrarily close to any particular unitary you'd like. On the other hand, things that are relatively simple that we'd like to use all the time can actually end up being rather long braids. The Ising anyons is quite nice because the connection to superconductivity means there are a lot more ways potentially to try to realize these in nature, and a lot more ideas about how to try to realize these in nature. On the other hand, braiding alone does not give us a complete set of, is not a complete set of gates. If we exchange these two in the sparse encoding, that you can convince yourself, is actually just what the F move does after all, because the F move changes you from a basis where these two have a fixed fusion channel to these two. So that's what's generally called the Hadamard gate. Okay. But that is what we really need to do. In addition, we need not only the Hadamard gate, what we'd also need is a controlled Z gate, which there is no way to make a controlled, so we need two copies of this qubit. There is no way purely through braiding to make a controlled Z gate. However, there is a way involving measurements. Okay. I think that Victor's probably going to tell me I'm out of time. I've long been out of time, so I'm not going to tell you about that now. And then the final thing that we also need is, and I apologize for the notation because we use T to mean another thing in this context, but there's a gate that's typically called the T gate, which is, which is this gate, which we also don't know how to achieve by topological means, although we can, if we have a noisy version of this, use braiding and these kinds of measurements to make it better. Okay. So with that, let me thank you very much for your attention. Apologize for running over.